Hi, this is Shelley Physics getting Kirchoff crazy today. As you see, we've got a really big circuit. It's actually a Crazaaay circuit. There are 6 unknown currents. There are all these branches of the circuit, and I want to show you how to solve this complex circuit as well as use matrix operations. There's a word. Use matrix operations to solve such a large algebraic system of equations problem. So we are also, of course, going to revisit Kirchoff's rules and how to use and apply the loop rule and the junction rule. So here's a circuit laid out. There are 3 EMF sources, a 20 volt source over here, a 10 volt source up there. It's a little bit hidden by the label, and a 25 volt source down here. We've got several resistors, 1, 2, 3, 4, 5, 6 different resistors. And if we look at all these different branches, there's quite a few. Now, if you count them right now, there are about 8 different branches. However, I am going to show you one little quality of this circuit that we can cut out, because sometimes circuits are presented this way, and I like to eyeball them and simplify them quite a bit. So that's the first thing I'd like to get to, is my circuit that I've drawn on paper looks similar but a little different. It looks like this. You'll notice a couple of key features flashing back and forth. You'll see the diagonal resistor over here. But you might notice that in the middle here, these 2 branches are sketched a little bit differently. Take a look at what I've done. I've taken those branches of the circuit that have no resistor or no battery on them. I've collapsed them down to a single point. That's right here, and also another point down right here. So please take a look at these 2 sections of the circuit. Now I'll talk about that. Oftentimes books or sketches or even test items would show those intersections looking like this. So what I've done is collapse these 2 points down, because if there's no resistance resembled or resistance put in between here, the circuit has no potential difference between these 2 points. So if there's no resistance or no battery there, no EMF source, there's absolutely no potential difference. So we could essentially combine these 2 points and cut out this little branch of nothing, of conducting material, and this little branch down here. So if you take a look, I'm going to squeeze this point to the left, I'm going to squeeze this point to the right, and same thing with these 2 points down here, squeeze them together. And so this branch with the 10 volt and the 2 ohm resistor and this 10 ohm resistor branch are going to be essentially parallel segments of the circuit, and that's how I've drawn it. I have them connecting here at the top and at the bottom. So the only difference is we don't have those straight segments going up. I have them meeting at one junction point. That's also called a node in the circuit, an ODE, node. So instead of 2 separate nodes, we've got 1 node down here. Instead of 2 separate nodes at the top, we've got 1 node. And we can see more clearly that there are 4 different branches coming off of that node or that junction. And down here, there's going to be 5 different ones. We can take one last look at this. Here we have the 1 at the bottom, the branch going to the left, 1 going up, 1 going here, that's 3, and the diagonal is 4, and the battery is 5 if we collapse that node. So that's one suggestion I would make if you ever see that pop up. It's okay to redraw that circuit. Just double check to make sure you've done it accurately. So let's go back to the paper. We're going to get ahead and solve this circuit. So what I want to do to start us off is bring back up that problem-solving method I introduced in the last episode. We're going to establish a direction of current flow for each branch of the circuit by drawing an arrow adjacent to and parallel to the resistors in each branch. So we'll put an arrow across each one. Number 2, apply the junction rule at unique circuit nodes to account for every value of all the branches. And then we're going to apply the loop rule for unique loops of the circuit until all the elements of the circuit are represented at least once in the set of loop rule equations. I'm going to talk quite a bit about that word unique circuit number 2, and unique loops of the circuit in number 3. It's really important to find those unique equations when solving this, or else you're not going to be able to solve it at all. You'll run into some stumbling blocks. So we're going to start by establishing a direction of current by sketching those arrows on here. Again, you can make a guess on all of them. What I like to do is try to guess them right, see if it's a little game I play. How's it going to turn out in the end? And if we end up with negative currents, it just means I didn't guess that direction properly, and we switch it for our final answer. So I like to start with the biggest battery, the highest EMF battery. That's this one. So if I'm thinking the current's flowing to the left, that means it's going to flow down across this 3 ohm resistor, and that would give a single direction of flow in this branch of the circuit. So parallel to the resistor and adjacent to it, there we go. I'm just going to label this I1. It's the first current I'm labeling. So here's another branch next to it. I'm guessing maybe it'll go in the same direction. So let's draw an arrow right here. I'll call that I2. All right. So I have these 2 currents flowing out of this junction up here, up top in the corner. So I'm going to mark the current I3 as going into that junction. Current in is going to equal current out. So I want to have at least one current going in. All right, I'm going to round about to this second largest battery. If the flow is going from left to right across it, from the negative to positive, then it'll be going from right to left across this 7 ohm resistor. So I'm going to label that. It's going to be my 4th current I'm labeling. And all right, so does that mean we're going to have maybe possibly a downward current through this one from negative to positive? So let me go ahead and guess that. Downward I5. So maybe that battery there is pushing current down this way. And okay, so if I've got I4 and I5 and I3 all going out from there, I might guess that the current is going up in that branch. So I'll call that I6, current 6. And there I've got them all labeled, and each branch of the circuit has a labeled current flow, and I'm going to make that my standard for the rest of the problem. I've established a direction of current flow for each branch. I'm ready to move on to applying the junction rule. So I want to find some unique junctions here, and unique meaning I don't need to write an equation that has the same exact current unknown I's as another equation. So I've got 3 possibilities here. There's a junction, here's a junction, and here's a junction. So I just start at the top here. I'm going to start applying Kirchoff's loop rule. Sum of the currents in a loop equal 0. So I always say that the current ins are my positives and the current outs are my negatives. That's just the way my brain thinks. You can make it the opposite if your brain thinks the opposite way. It's fine. They all equal 0. So algebraic equations will all be the same if you pick positive in or out being positive. So my ins, I've got an I6 going into this junction. So I'm going to start with an I6. This is going to be my first equation. And that one's going in, and I've got 4, 5, and 3 all going out. So I'm going to subtract them all as the current's going out. 4, 5, and 3, there they all are, and all that should equal 0. Just want to double check. I6 in is positive, 3, 4, and 5 all negative going out from this junction. So there's one equation in motion. Well, let me take a quick step back here. How many equations do I need? Since there are 6 unknowns, I have to find 6 equations. So I've got one already, and we can try out another one of these loops. So my second one, I'm going to pick. It's either going to be this one or this one. That's important to make a distinction of. If you look at the one down here, you've got current 4 coming in, current 5 coming in, 6 going out, 2 going in, and 1 going in. The only one we're missing there is current 3 up here. All right, but 3 we've already got covered here in this first equation. So all we need is something involving at least one of these currents. We need a junction that involves one of these, and current 1 and 2. Those are the only numbers we're missing. So I look over here, and this junction also has 1 and 2, and one of the currents from over here. That would make sure that would ensure that we have all of the current branches covered. So this one's a little shorter. There's only 3 branches, so I'm going to go with that one instead of this 5-branch junction. So here I've got I1 and I2 going out and I3 going in. So I'm going to have an I3 going in minus I1 minus I2, all equal 0. Okay, so that's my second equation. All right, now moving on to the loop rule. Just going to grab another sheet of paper so we can keep that focused. All right, so Kirchoff's loop rule, sum of all the potentials in a loop equal 0. Very creative guy. All right, so since we've got 2 equations, and this third one would have been kind of a repeat of the others, because we've got 2 already that cover all those I's, we don't want a third from that one. It's not going to be unique. We'd get some result like 2 equals 2 or something lame like that. It's not going to be very helpful. So for our loop rule, we're going to need 4 different equations to fill out our 6 equation requirement to solve for 6 unknowns. All right, so what loops to pick? Well, if I start, let's say, just in the bottom corner here, I could do the outside loop. I could do a loop that goes like this through the diagonal and back. I could go right here, and I can go right here. You could start in the same point each time and get your 4 different loops, and that would ensure that we have all of the resistors and all the branches covered there. We could do an inside loop like that. I could do this. I could do the middle one. I could do this Argentina-shaped branch of the circuit there. Or is that swooping the wrong way? No, that's about right. And I could do this triangular loop there. So there's a lot of possibilities and probably 12 different combinations of what you can pick out here. So I like to start behind a voltage source. So mine start in this corner here. And for my first loop, I'm just going to go up through here. I'm keeping it close to home. So our third equation is going to start with a loop. We're going to go from a negative to a positive side of the EMF. So that's going to be a positive change in potential, positive 20 volts. Now, okay, I'm going to cut back this way. I'm going against my established flow. So if I'm going against that, then this should be the higher potential, and this should be the, going the other way. This should be the lower potential, and this should be the higher potential. We're going downhill this way is the analogy to like gravitational potential. Downhill would be a negative change in potential. So here we're going uphill, that would be a positive change in potential. So I'm going to add the potential across a resistor is IR, V equals IR for a resistor. So we're going to add I5 times R is 2. All right? That's the IR for resistor of 2 ohms. Now we're going from the positive side of this EMF to the negative, so that's again going to be a negative change. My flow is going against the my loop is going against the established flow of charge there, of current. And so we went through the 20 resistor, battery. Now I need to go back to my starting point again through the 7 ohm resistor. But now I'm going with the established flow of current. That might be a little redundant, that's okay. So we're going across the resistor from the higher potential to the lower. So that's going to be a negative change of I4 times a resistance of 7. And that'll bring us back to the same point again, starting point. So there's a 0 sum to that potential in the loop. All right, fourth equation. Need another loop. I'm just going to reuse the same one. I'm going to go up, but through this part. So we're going to start the same way, 20 volts. But now I'm going in the correct direction. So we're going to subtract I6 times 10, and I'm going to subtract I4 times 7, and all that equals 0. All right? There's 4 equations. Let's get another loop. All right, I'm going to try some shorter equations here just to get some short ones going. Looks like there's a little circular loop here, and that might indicate that I have a direction incorrect. You'll see that in a moment after this equation comes out. So if I start right here, I'm going to go up across I6, across I3, or take I3 and then take I2 all the way around. Feels like I'm taking a road route here. So I'm going to take the I6 past 10 ohms, but I'm going from higher potential to lower, dropping, so this is going to be a negative. And then we're going to go this way, minus I3 times 8, and then minus I2 times 5. And I'm back to the start again. So all that equals 0. So you can see here, one of these signs is probably incorrect. You might have guessed now, we'll find out in the end. And sixth equation. Now when you're working this, you don't need to put these numbers on. That might get confusing for you, but just for presentation's sake, I'm labeling them to show that we'll have 6 equations after this one. All right, so I'm going to start behind the battery. That's my favorite thing to do, and go this way and up and down, back around. So we'll have a 25 as we go across it from negative to positive. Here we're going against the established flow, so I'm going to add I times R, and then with the established flow, so minus I1 times 3 equals 0. All right, fun. And so assuming I got all my signs right and didn't put a wrong resistance value in or something like that, I'm kind of done with the physics. Right now, it's a big bloated math problem. So we have 6 equations to solve for here, right? And they should all be unique. As you saw, as I went across the circuit here, I tried not to overlap anything. You can kind of see how the equations are going to combine here. You see the common 7 and 20 with the first 2 equations. The first loop I took through here, second loop was through there. Those 2 equations are going to be combined or linked by that 7 and 20. The second and third equation is going to be linked by I6. My second equation took this loop, and my third equation took this loop, both through I6. And both equations, my third loop equation and my fourth loop equation, both had I2 as their common linkage. So those are all unique. I covered all the resistors, all the EMF sources, so we should be ready to go. So the first thing I'm doing and thinking as I'm looking at these is I don't want to solve 6 equations with 6 unknowns. I could stack them all, but that's going to create new equations, or I could solve this by substitution, and I just think that there might be a simpler way, and yes, there is. If you've ever taken a class and learned matrix operations, you might recall this method, but I'm not going to go through why it works or how it works. I'm just going to show you how to do it because it's just a lovely simplified way to solve this. And there's one thing we need to do though is set it up. So we need to make all the terms agree with one another, put them all in the same order. We're going to put all the I1 terms in order. We're going to put all the I2, 3, 4, 5s, and 6s in order, and all of our coefficients that don't have an I term, that aren't multiplied, so like our 20s and our 10s, we're going to put those all on the other side of the equal sign. So here I go. First I'm going to order this first equation. Actually, I'm going to use equation 2 first because it has an I1, 2, and 3. So I'm going to keep those signs and make sure I record these correctly. Got a negative 1, I1, minus I2 plus I3. It's really important to keep those coefficients, like the negative ones and the positive ones, out there. Now there's going to be a slot for a 4, a slot for a 5, a 6. So there's going to be equal sign out here and 0. I'm stacking them all up here. Next one. If you're unsure about what I was talking about here, here's what I was talking about. This equation, we've got a negative I3, stacking it under the I3 from the previous equation, negative I4, negative I5, and a positive I6 equals 0. All right? So there we have the kind of placeholders there. Equation 3, we've got the 20. I'm going to place that 20 over here. And, oops, excuse me, 20 minus 10. Okay, and that equals 10. All right, almost messed that one up. And we've got a 2i5. So I'm going to put a 2i5 right there, a plus in front of it. And a negative 7i4. There we go, that's the third equation. See, I'm not relying on my artistic or writing talent here. Okay, so the equation 4, we've got 20 and no other numbers by themselves, and negative 7i4 again. And we here have a negative 10i6 minus 10i6 equals 20. So these are still the same equation. Equation 5. Got a 0 at the end, so I'm going to leave that for last. I got a 2 term and a 3 term, so negative 5i2 and a negative 8i3. And we've also got a negative 10i6, all equal to 0. And finally, a 25 on the end, negative 3i1, and 5i2, so plus 5i2. All right. Now that may look a little funny to you, but what we really have in here is a bunch of zeros as well, plus zeros. So the zeros are placeholders for our matrix system of coefficients. I might have just made that up, or that possibly could be the correct or valid term. I have no idea. All right. So now the fun part. Take out your graphing calculator. You do need a graphing calculator for this one, not scientific. All right, mine is on an iPad here. Turn the light out. All right. So yours should look similar to this. We're gonna look for this matrix button here. It's usually hitting the second key and then matrix. Now the first matrix we're gonna make is a 6 by 6 matrix. 1, 2, 3, 4, 5, 6 across and 6 down. Actually, I believe we'll see which one's first. The second matrix we're going to make is a 1 by 5, or I think it's a 5 by 1 matrix is how you'd say it. So 5 down and 1 over. All right. So let me clear that. Second matrix. I'm going to edit. So yours might look a little bit different. You might have an edit key. Just use the prompts on your calculator to work this out. And we're going to edit matrix A. We're going to make it a 6, enter. So the 6 gives you the number of rows and 6 columns across, enter. So you see I have a whole bunch of data to enter here, and they're all zeros to start with. But what I'm going to start doing is just plugging in the coefficients in front of each term. Now if there is no term, we're going to put a 0 in. So 0 is the coefficient in front of I4 here. Totally makes sense. But a -1, -1, +1. That's how I'm going to start out in that first box. a -1. I have to plug it in correctly. And just push enter and it goes over to the next part. And I'll try to move through this quickly here because otherwise it'll take forever in the video. And the rest of those are 0, 0, 0. So if I push enter, it will eventually get me down. And maybe I was hoping too much. Yours is probably going to go to the next row. Mine didn't. Number 2, I've got a 0, 0, -1, -1, -1, +1. All right, so 0, 0, -1, -1, -1, and +1. That one worked that time. Maybe I need to plug in 0. Probably didn't work before. All right, and my third row, 3 zeros, a -7, a 2, and we're gonna come to this 10 later on. That's actually not part of it, so we're just gonna have a -7 and a 2 for the 4 and 5 terms. So enter. Looks like I pressed some buttons through the paper. There we go. 0, 0, 0, -7, 2, and 0. My fourth one, and it looks very similar. All right, we've got a -7 and a -10 in that fourth row. -7, 0, -10. All right, number 5, we got -5 and -8 and -10. Got a 0 for the first one, -5, -8, skip 2, and -10. And finally, the last row, -3, 5, and the rest are zeros. All right, and that should be my matrix, correct matrix values there. Just double checking a couple of them. Looks like I got the signs right. Okay. Now you had second quit. So you're quitting out of that. Don't worry, it's stored in there. We'll go to second matrix once more. And we're going to edit again, but edit B. And this one's going to be 6 columns and 6 rows in 1 column. So 6 by 1. 6 by 1. And now all I'm going to do is go down 0, 0, 10, 20, 0, 25. 0, 0, 10, 20, 0, 25. All right. Now it's magic. We're going to go back to that matrix, but instead of going to edit, we're just going to use the name. All I'm going to do is touch that. And this is the matrix operation. We're going to take the inverse of the matrix. I think there's a fancy name for that. Inverse of matrix 1 times the matrix 2. Inverse of matrix A times matrix B. And what this does is it does all that number crunching for you. And do you see those numbers there? That should be the result of these currents. All right. Now, unless I got some numbers wrong, looks like I might have picked some directions incorrectly. All right, so I'm going to slide this down so you can see my circuit. Now the top one is corresponding to I1. Okay, so I1. So this is showing a negative flow upward. All right, so an I2, is this what I would expect? So this is not what I would expect. And perhaps I'm doing I had a lot of these wrong. I was expecting some of these other ones to be incorrect. What about I4? I4 added backwards also. So there's a couple things not adding up here, which might make me look back at some of my numbers and make sure I plug them into the matrix right. And then if I don't find an error there, I'll probably look back at my equations to make sure I'm not missing a negative or a positive somewhere. It's usually what I do. But the 25 and the 20 volt should be pushing pretty well, but this is showing that I1, this current coming down here, is actually going the other way. It's also showing that I4 is going the opposite way, because there's a negative for that fourth one and a negative for the first one. I have a lot of negatives on here indicating I guessed the wrong direction. This is part of it. Evaluate your answer. Sometimes you just can't go with the numbers that get. That's what it is. Evidently, Scholle physics is not Scholle math, because what did I do? Of course, you guys probably saw this as I was working it through. I have to subtract this. All right, so this should be a negative 20 and a positive 10. So that should be a negative out here. All right, and got to bring to the other side. And likewise on these, the 20 and the 25, both those should be negative. So after all that, make sure you're not talking while you're doing your math, okay? Because it's easy to miss a sign in algebra. All right, so we're going to plug those back in and see what we get here. These are going to be some negatives. Negative 10, enter. Negative 20, 0. Negative 25. All right, now we're going to try out that operation again. I'm going to hit second entry. All right, let's try it again. Oh, that looks so much better. So now we have some positive values. Maybe I got a negative for I2 and a negative for I5. Let's check those out, see if those make sense. Negative for I2 and for I5. So it looks like I5 is going the other way, and I2 might also be going the other way. So I'm going to turn it to an X and make that an arrow. All right, just corrected for that. And for my values, here they are. I1 is 3.4 amperes. I2 is 2.95 or 96. I'll put a 1 there. Use 3 significant figures. I had no measurement, so it doesn't matter too much. And then 0.4498, I'll make that a 450. 1.26 amperes. I5, 0.591, and I6, 1.12 amperes. All right, let's go to the simulation and check it out. So I've got on this side 3.4, 2.96, and 0.45. Let's check those out. I'm going to use this magic current meter. It just kind of examines the different sections of the circuit. My I1, 3.41, I2, 2.96, and this was 0.45. So those check out perfectly. Then we've got the current across. This would be I6. I'm guessing 1.12 according to my paper. Yeah, sure it is. And through the next segment, I5 is 0.591. There we go. And I4 is our last one, 1.26. There it is. So that worked out perfectly, except for just a little bit of algebraic math problems there. Scholle's got games, Scholle's got physics, but not so much on perfect algebraic work there. But this is probably long-winded and takes us a while, but I hope you picked up a lot of confidence from this. Make up your own circuits. These are really fairly simple to make up. Start it with like a figure 8. Make sure there's a resistance on each branch. having something like this gets a little funky at times. But just remember, every battery has an internal resistance, so there's always going to be resistance in every branch that has a battery. Include one, even if you call it the internal resistance of the battery. Include a little resistor in there, make up your own circuits, and I really highly recommend using phet.colorado.edu. Find their circuit construction kit, and you can just simulate the circuit that you create on paper and use the current meter like it did. Just look up those values. All right, it's very easy to practice and make your own circuits. Of course, you can also look in your textbooks. But this day is brought to you by Octopi, because we had the virus set in. A couple of weeks prior to that, we did have Pi Day, but it was on a Saturday this year. So unfortunately, I didn't get to celebrate at school. But hope you enjoyed the session. This is Shirley Physics, getting crazy with Kirchoff. All right, take care.